Hey guys, welcome to the next video set in the acids and bases set. So today we're going to be going over a specific kind of problem that comes up pretty often on exam 1. So we're going to be going through that. If you want to maybe pause the video and try it for yourself first, and then you can use my video to check over yourself, please feel free to do so. So let's get started. So the question asks us to draw the most stable resonance structure of the product of the following acid-base reaction. Okay, so we have this carbon chain with a carbonyl on it and a double bond within this compound reacting with an OH minus, which is a base. It's a hydroxide anion. And so it's an acid-base reaction, so we know that a base is going to be taking a proton and the acid is going to give off the proton. All right. And when we do this sort of question, the whole point is that we need to find the most acidic proton on this, or the most acidic hydrogen on this compound. All right. Before we do that, I'm just going to talk very quickly about the carbonyl functional group and just some sort of nomenclature you guys might encounter through TAs or just on the test. So here's our carbonyl. I'm just going to draw a chain out here. All right. So the part of the carbonyl right here, this is the functional group. It's okay. It is a carbon double bonded to an oxygen. All right. And so when we're talking about a carbon atom bound to a functional group, we denote that as as we call it an alpha carbon. And so this carbon right here is part of the functional group itself. So that is not the alpha carbon because the carbonyl has a C in it. It has that C double bonded to the O. So that is not the alpha carbon. This is going to be the alpha carbon right here because it is because that carbon is going to be bound to that carbonyl carbon. Okay? The carbon adjacent to the alpha carbon is called a beta carbon. So that's the beta carbon. And the carbon adjacent to that is the gamma carbon. All right, and we can keep going on forever, like alpha, beta, gamma, delta. All right, and so the same applies to the other side. So we have our alpha, we have our beta, and then we have the gamma. All right, and this sort of nomenclature holds true for when we're talking about carbons bound to functional groups. Okay, and so if I had, like, let's say this carbon chain here with a chlorine, the chlorine is the functional group itself. And so in this case, this is going to be the alpha carbon. All right, that's just some quick nomenclature you guys might encounter, so it's useful to know that. And also the two types, well, some of the types of carbonyls you might encounter. We have this structure where these are carbon chains. That's called a ketone. When we replace one of these chains with a hydrogen, that is called an aldehyde. Okay? So that's just some quick nomenclature I just wanted to get out of the way. It's useful to know these functional groups because they will come up in Orgo 1 and 2, so I would just get used to them. All right, so in this question, the whole goal is to find the most acidic hydrogen, right? We have a base. The most acidic hydrogen is going to be the one that's the most easily given off and taken by the base, okay? And so if you guys remember from the ARIO videos, the more acidic hydrogen will result in a conjugate base that is more stable than the other hydrogens. So in reality, what we need to do is we need to find our most, the hydrogen that when we depronate it will give us our most stable conjugate base. Okay, so the way we can approach these problems is we can take each hydrogen one at a time and draw the conjugate base and see what we get. Okay, so let's see what we have over here. So let's start off with the aldehyde hydrogen. So I'm going to start off over here. So let's draw a curved arrow. Right, we're going to go grab the hydrogen. And you want to break that hydrogen carbon bond because we're taking that hydrogen, and hydrogen can only have one bond at a time. So we're going to have an arrow and that carbon. Should have drawn that better. Okay, and so let's draw our structure. And I'm only going to be drawing the hydrogens that we're focusing on at that one time. Okay, and so we ended up with this structure where we have that carbonyl, that carbon double bond to the oxygen, and a lone pair on it. Okay, and so when we have when we have a lone pair on this carbon with a double bond, we can't resonate that lone pair. It's not within the it does not line up with the p orbitals. Sorry, the orbital that lone pair is in cannot resonate with that oxygen and that carbon. Okay, and so essentially this can't be stabilized through resonance. So the only reason, so we have a sp2 carbon. This is sp2 right here. Okay, and that is the only defining characteristic of its acidity. That negative charge cannot be stabilized through resonance. All right, and so it is just a general rule that the aldehyde, oh, not a general rule, it's just something that's quick for you guys to remember, that the aldehyde hydrogen is never the acidic hydrogen. It is never going to be deprotonated. It is not acidic at all. It's got a very high pKa. And so if they ever give you an aldehyde for one of these questions, you can pretty much eliminate that right away, that it's never going to be the acidic hydrogen. Okay? And so we can cross that one off our list. Alright, so I'll just put an X. Alright, so let's go to the next one. Let's go to this one. Let's draw a curved arrow. It's going to attack that hydrogen, and we're going to form a lone pair on that carbon. Oh. Okay, so there's our lone pair. Now this is similar to what we said before. We have a lone pair on a carbon that's double bonded. That lone pair cannot participate in resonance. So essentially we cannot shift that negative charge around, or we cannot delocalize it, and so it's confined to one area. The fact that it's confined to one area makes this structure unstable. Okay, so remember that we want to be able to delocalize our negative charge, and so the fact that we cannot delocalize the negative charge means that it is not going to be acidic. And so that's essentially rule number 2. Hydrogens of carbons with a double bond are also not acidic. And so if we just number this, number 1, aldehyde H, not acidic. H on carbon with a double bond, not acidic. Okay? And so we can cross that one off our list. That one isn't going to work either. So that. And we can skip a step, because this hydrogen right over here is also just right off of a double bond, a carbon with a double bond, so we can eliminate that one as well. So now we're left with our last option, so let's draw the curved arrow. Pick any one of the hydrogens, it doesn't matter. Okay, so we have this carbon with a negative charge, and yeah, and so we want to see if we can resonate that negative charge. All right, with these questions, they will usually be giving you a carbonyl on this functional group, and you want to be able to resonate that negative charge to that oxygen. Oxygen is much more electronegative than carbon, and can better stabilize that negative charge than a carbon can't. Than a carbon can. Carbon is not good with a negative charge, it's very unstable. Okay, and so let's see if we can resonate this. If we look at this carbon right over here, it has a hydrogen, and it's double bonded to another carbon, and it's got that single bond to the carbon with the lone pair. So what we can do, and if you want to again pause the video and practice, finish this question off to practice your resonance skills, please feel free to do so. So what we can do is we can take this negative charge, that lone pair, form a pi bond there. Now the problem is this carbon with that that I marked in green is going to have too many bonds if we just did that. So what we can do is shift this double bond over here, and again, same thing, that carbonyl carbon would have too many bonds, and so in order to make sure that no octets are broken, you bring that double bond up to that oxygen, and we get this resonance structure. All right, so that's our resonance structure. And so here we have an oxygen with a negative charge, great, and we were able to delocalize that negative charge on the carbon, great. And so because we were able to do that, we know that this, or any of these 3 hydrogens, are the acidic ones. Okay? And so once we figure that out, you just want to deprotonate it, and we got this structure. And because they asked us for the most stable resonance structure, we had to go from this structure and then draw our resonance structure. Okay? And so that's how we go through these problems. And just one quick thing, sometimes on these questions they'll ask you to draw the curved arrows as well, and they'd want you to do it all in one step. So we showed it in sort of 2 steps here. One where we deprotonated the hydrogen and gave the carbon a negative charge, and the second step is resonating that negative charge. They want you to do it in one step for the whole thing. So let's just try to do that really quickly, just so you guys are prepared if they were to ask you this. So we know that our first arrow is going to be deprotonating that hydrogen. So we would draw this. And now the way we did it before is we broke this bond and brought it onto that carbon, right? And then when we were doing our resonance arrow, we had a negative charge here, and we formed the bond there. Well, what I'm going to do is, instead of drawing that purple arrow going to the carbon, right, I'm going to draw it forming the double bond already, because remember, we have 2 electrons here. So I'm going to skip straight to forming that double bond. Then we can shift that. Then we can kick that double bond up. And then we'd have our resonance structure that we showed before. Okay, so that's how you do that. Now I'm going to talk about one quick other thing that can save you some time when doing these questions. So let's say they gave you this molecule, and we labeled them alpha, beta, gamma. So a quick way that we can skip ahead with these is that the alpha carbon, right, is usually acidic, depending on if it's double bound to if it has a double bond. All right, if we have this double bond here, it's not going to be acidic. Okay, because again, remember, we'd have the negative charge on a carbon that's double bonded, so that's not great. The beta carbon is never acidic, no matter if it has a double bond or not. Because let's say I remove that double bond, we have these 2 hydrogens over here on this alpha carbon. All right. And so because we have those 2 hydrogens, if I had that negative charge on that beta carbon, I can't resonate. I can't do that. And let's say I had a double bond there instead. So I just put that double bond. Can't resonate that either. Right? And so that's not going to be acidic at all. So that can save you some time. The beta carbon is never the acidic one. Alpha is sometimes. And the gamma carbon is sometimes acidic if it can resonate to that carbonyl. Alright, so we have that negative charge here. It's sometimes acidic as long as it can get there. In this case, because we have the double bond, we can resonate it. But if I remove that double bond, well, then we can't resonate because we have 2 hydrogens there, 2 hydrogens there. Okay? And so that just may save you some time on the questions if you see this on the test. And so if something in this video didn't make sense, please feel free to email me. Go to the office hours. The TAs are there to help you guys. They'd be happy to help you. And yeah, I'll see you in the next video where we will be covering pKa's and some of those questions you might have seen about the amino acids Alright? And it's good practice if you're going to be taking biochem in the fall or summer. And so I'll see you guys in the next video.